is the linearity property. Consider two Fourier series with respect to some period t naught. Let's say it is ak and x2t. If x1t is periodic with period t naught, x2t periodic with t naught, what about x1t plus x2t? It is also periodic with same period, isn't it? Is it? Consider two periodic signals having period t naught, and if you add these two, that is also periodic with period t naught. So we can have a Fourier series representation. Now, how are they related? Is it AK plus BK?
Yes.
It is very easy to prove. This implies that x1t
Right only want to
this implies that x1t is equal to sum of k minus infinity to infinity ak e to the power j k omega naught t, and this implies that x1t bk e to the power j k omega naught t, isn't it? Now suppose this x1t plus x2t, it is having a Fourier series representation ck. What does it mean? x1t plus x2t, that can be expressed as ck e to the power j k omega naught t. That is a Fourier series representation. Fourier series representation of this periodic signal. Now, if we add these two and equate that summation with this, what will you get? Will you get this relation?
Yes, sir.
Okay. So that is the additivity property, and linearity property. You have to prove this also. If you multiply with a constant, let's say I'm multiplying with a constant. Is it this? It is straightforward. I'm leaving it as an exercise. That is a homogeneity property. If you scale with a constant, Fourier series coefficients are also scaled by the same value, same amount. Okay, so we can summarize that linearity property. If x1t Fourier series representation with respect to a period t naught is ak, and x2t Fourier series with respect to period t naught bk, then x1t plus x2t, a times x1t plus, let's say, b times x2t. It is also periodic with period t naught, and its Fourier series coefficients are that is the linearity property. And the important thing here is that this is valid only when we are considering the Fourier series representation with respect to a same period. With respect to the same period, all these t naught are equal. Otherwise, it is not valid. For example, if this is Fourier periodic with period t1, then can we add these two? Add these two and equate to this? Will you get this relation? What is omega naught? Omega naught is 2 pi by t naught. If this is periodic with t naught, then omega naught is this. And if this is periodic with t1, then what about this? Is it 2 pi by t1? So you cannot directly add those two and equate with this. You won't get this relation. You can add and equate with this, but you won't get this relation. So that is an important thing to remember. This linearity property what I explained, this is valid if you are taking Fourier series representation with respect to the same period, then only it is valid. Okay. Now I'll give you some examples, and there are many examples, many problems related to these properties in the second and the third tutorial sheet. Okay, let us say okay. Can we use the periodicity, this linearity property here? The period is
Yes, sir.
what? T naught, and so T naught is 2. This is T naught is 2. What is the Fourier series representation with respect to this period? Sin pi t. I am simply writing this 1 by 2j minus 1 by 2j, assuming that all the other Fourier series coefficients are 0. And what about this? 1 by 2. This is also 1 by 2, right? Now using the linearity property, these two are the Fourier series representation with respect to the same period 2. So we can add these two. So this is what? What is the Fourier series coefficients of this? Is it 0, 1 by 2 plus 1 by 2j? Then all are 0. Here it is 1 by 2 minus 1 by 2j. Is it this?
Yes,
We can directly use the linearity property. Okay. Now, if we consider this, if let's say xt is its Fourier series coefficients with respect to period t naught is ak. Now, can you tell me what about this? If you are adding a constant to that signal, if xt is periodic, if you are adding a constant value to that signal, will it be a periodic signal?
Yes, sir.
sir.
Constant value means it is a DC shift only, isn't it? Periodicity will remain the same. It is periodic with the same period. So let's say its Fourier series is, how are they related? Can we apply the linearity property here? What about a constant signal? Is it a periodic signal? Is it a periodic signal?
Yes,
It is. We can consider it as a periodic signal with any period, isn't it? Is it?
yes,
We can
yes,
consider it as a periodic signal with any period. So if we want to apply the linearity property here, we have to find the Fourier series representation with respect to what? Which period? This is having a period t naught. Let's say ak are the Fourier series coefficients with respect to that period t naught. And if we can find the Fourier series representation of this constant with respect to this same period, we can directly add those two using the linearity property, isn't it? Is it? Now tell
yes,
me, what is the Fourier series coefficient representation of this signal with respect to t naught? What is the expression? What is the Fourier series analysis equation? AK is equal to what? So, okay, so I'm writing it as BK is what? How to get that? Let's say this one is BK. What is that? Integration over one period. Then the signal into e to the power minus j k omega naught t. Is it that? dt. That is the Fourier series analysis equation. Can you tell me what is this integral? How many non-zero values will be there?
1.
What is B0?
C.
B0 is C. And then
Other 0.
all other values are 0. Bk is equal to C for k is equal to 0. And it is 0 for... It is easy to verify that, isn't it? Because this is a periodic signal. E to the power minus j k omega naught t is a periodic signal. And what is the fundamental period? What is the period of that? What is the period of this k omega naught t? Is it T naught or T naught by k?
T naught by K.
If you consider the kth harmonic, the period is k naught by T naught by k. And you are integrating it over T naught. So the sine and cosine, that imaginary part is sine and, real part is sine and imaginary part is cosine, real part is cosine and imaginary part is sine wave, isn't it? So you are integrating both with respect over a period T naught. So how many periods you are integrating that? If the period is T naught by k, if you are integrating in an interval T naught, so can we say that we are integrating that sine and cosine signals over a period? How many cycles? K complete cycles?
Yes, sir.
So that will be 0, isn't it? Now tell me, what are the Fourier series coefficients of this xt plus c? I am denoting it as ck. Using linearity property, we can write it as ak plus bk. So can we say that this is ck is what? How many non-zero values are there for this constant signal? Only? Only one value. So can we write this as ck is ak plus c when k, and for all other values it is ak. So we can say that only this value, zeroth Fourier series coefficient is affected if you add a constant value to that signal, isn't it? All other Fourier series coefficients will remain the same. Is it? And it is easy to verify also, like what about let's say xt Fourier series T naught ak? What is the significance of this value a0? Zeroth Fourier series coefficient. And here we get ak as 1 upon T naught integration over T naught xt e to the power minus j k omega naught t dt. That is a Fourier series analysis equation. What is a0? Is it 1 upon T naught integration over T naught xt into what? What is that? When k is 0, is this 1? Is it a0? This is the synthesis analysis equation ak. We get like this integration. And if you put k is equal to 0, is it this? What is this integral on, what is this term on the right hand side?
Integration over 1.
Yeah, that I know. What is the significance of that?
Average value over a
It is the
period.
average value of the signal over one period. Or it is the average value of the signal. Is it? It is the average value of the signal. Now, if we are adding a constant value to a signal, what will happen? What will happen to the
The
average?
average value shift by that constant.
The average value shift by that constant. That is what is happening here. The average value shifts by that constant. Okay. Okay, so this linearity property, remember this linearity property is applicable only when consider the Fourier series representation with respect to same period. Now let us consider an example. Cos 2 pi t, let's say cos pi t plus cos, let's say pi by 2t. Can we apply the linearity property here? Can we apply the linearity property? That means, can we find the Fourier series of this and Fourier series of this, add those two? Is it?
Yes, sir.
Yes?
Yes, sir.
What is the period of the signal?
Sir, 2,
And what about this?
1.
Huh?
So fundamental period is 1.
Uh-huh.
So, but we can make it to a period
Is
of
it
2.
is it one?
4, sir, it is 4.
It is 4. It is 4, isn't it? Is it?
Yes, yes, sir, yes.
So can we directly apply the linearity property here? If we find the Fourier series coefficient of this, Fourier series coefficient of this, add those two, will you get the Fourier series coefficients of sum of these two? No.
No, sir.
No. You cannot add it directly. If this is a signal cos pi t, if we can find a Fourier series representation of this, look, this signal is having fundamental period 2. Is this also periodic with period 4? If it is period with
Yes.
period
Yes,
2, it is also periodic with period 4. So if we can find the Fourier series representation with respect to period 4, then we can apply the Fourier series, this linearity property directly, isn't it? Is it? So what I'm saying is, if we have a periodic signal xt, and let's say Fourier series representation, let's say its fundamental period is t naught. This is ak, and this implies that xt can be represented as summation over k ak e to the power j. This is omega naught is 2 pi by t naught kt, isn't it? Omega naught is 2 pi by t naught. Now the same signal, it is also periodic with, let's say, I am just giving an example to generalize this. Is it also periodic with 3 t naught? Forget about this example. I am considering a signal xt that is having fundamental period t naught, and if we are finding the Fourier series with respect to that fundamental period, this is the expression. This is xt. Now we can consider this as a periodic signal with period, let's say 3 t naught also. Is it? Xt is also periodic with 3 t naught. Now if I am saying that with respect to this period 3 t naught, Fourier series coefficients is bk. Is there any relation between these two? What does it mean? If it is with respect to period 3 t naught, it is bk. Does it imply that xt can be expressed as what? E to the power j? With respect to which period we are considering? 3 t naught. So we can write it as 2 pi by 3 t naught kt. Is it this?
Yes.
Yes. If we consider Fourier series with respect to period 3 t naught. Now this is xt, this is xt. Can you tell me what is the relation between ak and bk?
So B3K is equal to AK.
B3k? What B3k? B3k is equal to? What is B0? First, let us find one by one. What is B0? In this, you have
A0.
to equate these two infinite series as That means you have to find the terms having same that harmonics, isn't it? You have to equate the terms with same harmonics. So B0 is A0. What is B1? When K is 1, that is B1. This is this. There is this term is the harmonic is what? 2 pi by 3 T naught. Is there any such term here?
No, sir.
No, it is not there. Then that is what?
0.
0,
0. Then what about B2?
0,
0. B3?
A1 equals to A1.
B3 is A1. And if you keep on doing that, B6 is what?
8.
A2. And negative side also you will get the you will get similar expression. Okay. So can we say that this BK is equal to AK by 3? What is the meaning of this? I think I have explained this when we discussed about discrete time sequence. K by M means we can generalize this. This is A K by M. Actually, this is the short form of this when K by M is integer. Otherwise, it is 0. Okay. When this is an integer, it takes that value. Otherwise, it is uh, 0. So is it this? BK is AK by 3? Yes or no? In this particular case? Okay, let me
Yes,
take
sir.
a new page. So what we have proved here is if xt is a periodic signal with fundamental period t naught, and let's say its Fourier series coefficients are ak, and we can consider it as a periodic signal with any integer multiple of t naught. For example, I am considering 3 t naught. It is also periodic with period 3 t naught, and let's say bk are the Fourier series coefficients, and it is related to this ak as, is it this? This is what we have proved. If we sketch this, let's say this is if you sketch ak, let's say I'm just sketching these values. Okay, this is 0 1 2 minus 1 minus 2, like that. Now can you tell me what is b0? B0 is what? If I'm sketching bk, this is 0. Is it a0? Is it same? Then we'll have how many zeros? 2 zeros. Then next value is what? Is it a1? Isn't it? What we have seen is b0 is a0, b1 is 0, and then b3 is a1, like that. Is it? So can we say that it is equivalent to inserting 2 zeros in between each Fourier series coefficient here? Is it that?
Yes, sir.
We are inserting 2 zeros. And we can generalize this. I am leaving it as an exercise. It is straightforward. If xt Fourier series coefficients are with respect to fundamental period t naught ak, and if we consider the Fourier series representation of that signal with respect to, let's say, m times t naught, where m is an integer, then it is ak by m. That means in the Fourier series representation, how many zeros you are inserting in between each Fourier series consecutive Fourier series coefficients? If you consider ak by m, how many
M
zeros?
minus 1.
There are n
M
minus 1 zeros. Let's say this is bk. So b0 is, this is a0. Then there are m minus 1 zeros, and next value is a1, like that, isn't it? There are m minus 1 zeros, and So that is the operation, is it? Okay. Now let us come back to this problem, like cos pi t plus cos pi by 2t. Can we use the linearity property here? Now, first let us find the Fourier series coefficients of this directly. What is the period of this signal, cos pi t plus cos pi by 2t?
4.
Fourier series with respect to t naught is 4. That period is 4. Let's say I am writing it as ak. Can you tell me what are the Fourier series coefficients ak? This means what? This can be written as summation over k minus infinity to infinity ak e to the power j. If we are considering Fourier series with respect to period 4, we can write it as 2 pi by t naught, that is 4 kt. Now equate these two. What is on the left hand side? It is e to the power j pi t plus e to the power minus j pi t by 2 plus e to the power j pi by 2t plus e to the power minus j pi by 2t by 2. Is it that?
Yes, sir.
Now equate these two terms, then tell me what are the Fourier series coefficients? How many non-zero Fourier series coefficients? How many non-zero Fourier series coefficients?
4.
There are 4 non-zero coefficients. Tell me which are those values. A0 is what?
0.
A0 is 0. A1?
Half.
Half. A2? You can see easily verify this. This is 2 pi by 4 is pi by 2. Then equate these terms. It is straightforward. A2 is half, isn't it? Is there any other non-zero value for positive values of this k?
No, sir.
No.
No, sir.
Then negative side, how many non-zero values?
A minus 1
2.
equals to half. A
A
minus
mi-
2 equals to half.
A minus 2 equals to half. So can we simply denote it by 1 by 2, 1 by 2? Is it this? This is A0, A1, A2, A minus 1, A minus 2. All other values are 0. Okay. This is the here we got the Fourier series coefficients by directly computing the Fourier series coefficients. Now let us apply the this linearity property here. What are the Fourier series coefficients of cos pi t? What is the Fourier series? What is the fundamental period of this? Cos pi t? T naught is 2. And what are the Fourier series coefficients? Is it this? Yes.
Yes.
And what about the second term, cos pi by 2t? It is a periodic signal with fundamental period. What? T naught is 4. What are the Fourier series coefficients? Is it this? Same. That is a property we have already seen. If you consider any cosine signal, and if you take the Fourier series representation with respect to period, that fundamental period, you will get the same Fourier series coefficients. Okay, that we have discussed in the previous class. Like when I mentioned that the Fourier series representation is a unique representation if we mention only the fundamental period or the period with which we are taking the Fourier series representation. Okay. Now, if we want to apply the linearity property here, we need to have the Fourier series representation with respect to the same period. Here, one period is 4, the other period is 2. So what can we do here? Can we find the Fourier series representation of this with respect to period 4? That is twice the fundamental period. What is that? Cos, my question is cos pi t Fourier series I am considering with respect to period 4. That is double this period. Then what is the property we just now proved?
We will insert 1 0
How
between
many?
two
Because we are taking twice the fundamental period, so we have to insert that that multiplication factor minus 1. So here the multiplication factor is 2. 2 minus 1, that is 1 0. So if we do that, then you insert 1 0. Is it? Is it 0 1 by 2? Then we can add these two directly, isn't it? Because these two are the Fourier series representation with respect to the same period, we can add it directly. Is it? Will you get the same result if you add these two?
Yes, sir.
Okay. So the point is you have to be careful while applying the linearity property. You can apply the linearity property only when you consider the Fourier series representations with respect to same period. If the period is not same, you have to convert find the Fourier series representations with respect to the same period and then add it. Otherwise, you'll get wrong answer. Without this inserting the 0, if you add these two, you will get wrong answer, isn't it? Okay.